Daryl, would you let me know when to start? I think Daryl is not online anymore. So, Dheeraj, would you let me know when to start?
Oh, yeah,
What? Oh,
sure.
wow.
So maybe we'll wait for a couple of more minutes for people to just join in and then we can start.
Okay. Yeah. Um, so I would just like to make the announcement that like if any of you have any questions in the middle of the presentation, you can just unmute yourself and like ask the question. I typically don't have internet issues. Yesterday was the only day I had internet issues, and I'm not sure whether today I will drop out or not. But if I do, then I'll rejoin immediately. Okay, so I think that's my cue to start. So, hello everyone. A little introduction of me. I'm Shrimai Prabhumoye. I'm a final year PhD student at Carnegie Mellon University. My thesis focuses on controllable text generation. I work with Alan Black and Ruslan Salakutinov during the course of my PhD. And one question that I would like everyone to reflect on is, should machines reflect the way humans interact in society? So keep that question in mind. We'll come to it later in the talk. We constantly author text, be it on social media platforms or personal opinions in the form of blogs, or personal or professional documents like OneNote and Google Doc, and the newspaper or Wikipedia articles. Very few of those ideas are original. We commonly assemble ideas from multiple sources and recast them to fit our application. For example, you may read a newspaper article and decide to write an opinion blog post on it, in which case you would borrow content from the newspaper articles and write it in your own style and structure of your blog post. But if you decide to write a Facebook post on it, then it'll still be in your own style, but the structure would be different of your Facebook post versus your blog post. And so the key to human like generation is style, content, and structure. So let's start with style, which is expressed in the choice of words or phrases, as well as syntactic structures used to convey the information. There are many definitions of style that are out there, and I don't partake in disambiguating them. But for my work, I define style as a group of natural language sentences that belong to a particular class or label. For example, do you want to say something in a polite manner? Do you have any code that we can look at? Or an impolite manner? Any code, or do I have to guess at how you did it? Now, content, by definition, human communication is a process in which we exchange some information. And yet, this behavior is something that we don't see in the NLG systems today. A lot of NLG systems hallucinate information. And so I focus my work on leveraging the vast amount of information that is present in the unstructured form, like Wikipedia, Gutenberg, Encyclopedia, or the internet itself, and use it for content grounded generation. So, for example, there is an article about this movie, The Notebook, to the right, and Alice has access to this article, and Alice has used information from this article, which is marked in red and underlined. For example, the actors that acted in this movie, or the ratings it got on Rotten Tomatoes, etc. Alice has used this information in the conversation with Bob. And now you can imagine building a bot which would leverage the information from this document, which is on your right, to give factually correct information to users. And finally, if you want to generate longer sequences, then you want to be able to do it in a coherent manner. You want to be able to order the information correctly. And if you look at structure in this manner, then every written form has some structure. For example, the Wikipedia articles have a timeline structure. The SAT essays that you write, the recommendation letters, the official documents, all of them have some structure. Here I give an example of a newspaper article which has an inverted pyramid structure. It begins with the lead, that is the most important information, like what, who, where, when, and how. It then diverges into the crucial information, or the main story or the argument of the article. Here it gives you the juicy details about who said what to whom, the pictures, the background, and everything. And at the end, it would give you links to other editorials that are relevant to this particular topic. So now, if you can control for style, content, and structure, then one of the most popular application is in chatbot systems. For example, if the user says, I have a talk to present today, and the bot says, best of luck, which is a very appropriate response, but it may not be in the style of the user, and it may not have the same impact. So it will not be of the style of the user. But if the bot knows that the user is a Star Wars fan, then the bot can respond by saying, may the force be with you. And that would have a higher impact on the user as opposed to saying best of luck. Now, if the user says, have you watched Avengers Endgame? And the bot replies by saying, yeah, I loved Bradley Cooper in it. Then this is wrong content because Bradley Cooper never acted in this movie. And it is very important that chatbots respond with factually correct information to build longer term relationships and trust. And finally, if the user asks, have you watched Avengers Endgame? And the bot says, yeah, I loved the movie. And the user asks for the story of the movie, then now the bot has the correct information, it has the correct style of the user. But if it does not generate the story in the correct order of events that happened in the movie, then it is of no use. As you can see in this example, this particular generated story does not tell the user anything about what the Avengers Endgame was about. And so it's important to generate longer sequences in the correct order of the information. And some of the other applications of controlling style, content, and structure are that you can use it to recommend formal language or language with particular attributes. You can recommend structural changes in your documents, like you can ask to move paragraphs. So one of the another popular applications is writing polite emails. So if you write an email request, then can you recommend the polite version of it? You can also use it for story generation, where you can control for the plot, that is the structure of the story, the ending of the story, the sentiment of the story, or the topic sequence of the story, or even the persona of the narration. But more importantly, you can use it for content generation in general. Like you can generate an entire website or description based on, you can retrieve relevant documents from the internet and ask to generate an entire description based on these retrieved documents in your own target style and structure. And so in today's talk, I'm going to cover my work on style transfer, content, grounded generation, structure, and finally I would open the floor for ethical considerations of this technology as well as my future work in this space. So are there any questions still here? I'm still audible, right?
Yes.
Okay, great. So I'll talk about my work on style transfer, and I'm going to present my ACL 2020 work on politeness transfer. So politeness transfer is the task of converting non-polite sentences to polite sentences while preserving the meaning of the sentence. So for example, send me the data becomes, could you please send me the data? And there are many challenges involved in this task of politeness transfer when you actually practically try to solve this task. I'm going to mention some of these challenges here. First of all, politeness is culturally diverse. So something that is considered as polite in one culture may not be true in some other culture. For example, usage of the word please to your closest friends is acceptable in North American culture, but it is considered rude in Arabic culture. Second is politeness is subtle, that it is not only about using words like please, sorry, thank you, but it could be also conveyed through more subtle cues like using indirect statements or using first person plural forms, etc. Also, the non-polite class is ill-defined. So I'm calling it non-polite and not impolite. And this is because there is existing literature which helps us to detect the presence of politeness. But it is very difficult to objectify the absence of politeness. And what I mean is that the non-polite class is very fuzzy. You can include rude or arrogant statements as non-polite, but you could also include statements which have slur or foul language. So this is like a fuzzy class. And finally, there is lack of data. That is, there is no large-scale annotated corpus which could have helped us to solve this task of politeness transfer. So here I present some of the ways we try to overcome these challenges and what did we do to overcome these challenges. So first of all, we fixed the setting to North American English speakers in formal setting. And this helped us to cater to the problem of cultural diversity. And also we mentioned that the models that would be trained on the data set that we provide will not be applicable to other cultures. Setting it in a formal setting helps us to define politeness more concretely. Second, we focus only on converting non-polite to polite and not the other way around. And this is because the non-polite class, as I mentioned, is very ill-defined. And finally, we focus only on converting requests to polite requests. And this is very important because there are statements like the sun rises in the east. Now, how can you make this more polite? Or there is no notion of making such statements more polite. And so we focus only on making requests or action directives from non-polite to polite requests. So here is the architecture we used for our study, and it's a new architecture that I'm presenting. So it's a tag and generate approach. First, we have a tagger. The job of the tagger is to add tag words at positions where the polite phrases can appear later. So for example, send me the data. If that is given as an input to the tagger, it would generate tag send me the data. So it's expecting some polite phrase before send me the data. And then we have a generator whose job is to generate context appropriate phrases in the target style, which is in the polite style in this case. So it takes the input of the tagged sentence and it generates, could you please send me the data? And both our tagger and generator are transformer models that are trained from scratch. They are 4-layered transformer models. So let's see, how did we curate our data set? We used Enron corpus, and this was because it gave us this good grounding to North American culture. It helped us to fix formal setting. And also, more importantly, that since it was an organization, we could find a lot of request emails that were sent that we could then make into polite requests. We used the politeness classifier presented in New and Bansal 2018, and we annotated the whole corpus for politeness scores, which are between 0 and 1. 1 being polite and 0 being not polite. And with this annotation scheme, we have 1.39 million sentences that are annotated for politeness. And so we train this pipeline, tag and generate pipeline, in a supervised manner. That is, we have created parallel sentences for both our tagger as well as our generator. And how we create that is something that I'm going to explain in this slide. So we take only the polite sentences, and we have a very high bar for politeness. We set the threshold to politeness score of 0.9 and above. So all the politeness sentences from the Enron corpus of 1.39 million sentences was retrieved. And now if you have a sentence like, could you please send me the data, which is a polite sentence, we identify the markers of politeness in this polite sentence, and we remove these markers of politeness, and that serves as an input to our tagger. If we replace these politeness markers with the tag token, then it serves as an output to our tagger, the target output, as well as an input to the generator. And finally, the polite sentence, could you please send me the data, becomes the output for our generator, the target output. And hence we have parallel corpuses for both our tagger and generator, which are trained in a supervised manner. And so here are the results for the politeness transfer task in comparison to 3 other prior models. We evaluate them on 2 dimensions. First is how well does it transfer to a polite request, and secondly, how well does it preserve the meaning of the input sentence. And as you can see, our model performs competitively as compared to the DRG model for the transfer accuracy metric. The CAE model gets a very high score in transfer accuracy, but these are automated metrics for preservation of meaning, that is blue, self, meteor, and rouge. And for all of these metrics, our model performed much better than all of the 3 models for preservation of meaning. And this is the kind of behavior that we want to see in our style transfer models, where it preserves the meaning and it performs competitively in terms of transfer accuracy. We also have human evaluations that we have presented in the paper, and we have presented results on 5 more tasks: the Yelp sentiment task and the Amazon sentiment task, which is positive to negative and vice versa, gender transfer task, political slant transfer task, that is Democratic to Republican and vice versa, and the captions task, which is factual to romantic to humorous and vice versa. And these results are shown in the paper, but they follow the same trend. That is, when it comes to preserving the meaning, our model performs much better than the previous 3 models. And in terms of transfer accuracy, it performs competitively. Here are some of the examples, and we have identified the politeness strategy that was learned by a model as a post-processing step. For example, usage of counterfactual forms like could and would are considered to be more polite, and our model learns that. Usage of first-person plural is considered to be more polite. And apologizing, that is not simply saying no, but like reducing the burden that you put on the other person and saying sorry, not yet, is something that is considered more polite. So with that, I finish my work on style. So do you have questions on this particular segment?
Hi, Shri. This is Pradeep. Right, a quick question. You have a decoupled architecture for the tagging and generation, right? What's the motivation behind doing that?
So the primarily, I think our motivation was not decoupling, but more like trying to have an intermediate representation that is realizable and that is interpretable. So, like, it's not a latent variable that you don't know what is happening, but more like you can actually generate it and see what whether we are actually removing markers of politeness and whether it's placing tags at the correct positions or not. So I think that was the motivation for decoupling it.
And were the previous models that you're comparing against, were they similar, or were they?
So DRG is actually DRG is the delete, retrieve, generate model, and that is actually very similar to our model. And we have discussed the similarities and differences in the paper, but the delete, retrieve, generate actually does exactly something similar, that it identifies markers of that particular style, input style. It deletes that. It deletes those markers. It retrieves phrases, words or phrases in the target style, and then it generates based on the retrieve phrase as well as the whatever remains after deleting from the input sentence. So it's a little different, but it is also the closest to our model.
Thank you.
Okay. Any more questions?
I have a small question.
Yeah.
How did you identify the politeness markers when you were generating the parallel data?
Yeah, right. So we used TF-IDF technique and basically comparing words or phrases that appear more often in one particular style corpus versus the other. And we also, based on these TF-IDF scores, we kind of convert it into a probability distribution by normalizing the TF-IDF scores. And yeah, we use that to basically identify markers of that particular style.
Oh, cool. That's interesting. Thank you.
Thank you.
Can I just have a quick question? So I haven't read the baselines that you compared with, but so you use the transformer. So I wonder how much of the improvement on some of the metrics that you presented might come from the power of transformer if the other baselines don't use transformer, and how much is from the design of the model.
That's correct. So the DRG model does not use a transformer, but there are two more papers after DRG which are like converting DRG into a transformer based DRG, which we have again discussed in the paper. And so actually one of them also uses a pre-trained model. I believe it was BERT that they use, and so they have also reported numbers, but they had not reported numbers on all of the 6 tasks. Like the motivation of the paper was to actually give a politeness transfer task along with a data set. And so the other 2 models which were using transformer didn't have numbers for those, but they had numbers for Yelp as well as Amazon. And so yeah, you can have a look at those 2 numbers. So yeah.
Great. Yeah, thank you.
Any more questions? Okay, then I will move to the next segment, which is I'm going to talk about my work on content grounded generation. So here are 2 examples. The example on your left is from a current AI assistant tool, and it helps you to correct errors of this form. But the example on the right, there is no AI assistant tool today which could help you to correct Carnegie Mellon University to Columbia University. And so our goal in this work was to control for content. And so our task is that if you're given a Wikipedia context, an existing Wikipedia article, which is something that happens most of the times, that you try to update existing Wikipedia articles based on the new events that occur as opposed to starting a new Wikipedia article. So if you have an existing Wikipedia article and now a new event occurs that is relevant to this particular Wikipedia article. So in this case, there is this monkey selfie copyright dispute, which had a lot of updates and events that happened over a period of 2 years. And so initial reports suggested that the monkey took a selfie of itself, and then there was a question of who owns the copyrights. And so there was a time when the photographer David Slater clarified that the monkey accidentally took picture of itself when the photographer was trying to fend off other monkeys, and that bit of information was important in the whole lawsuit. And so can you generate the update that came from this news article that was relevant to this Wikipedia context? That is, can you generate text that is coherent to this Wikipedia context and contains new information from the news article? So to reiterate our task, if you have a curated text or a summary, in our case, it's a Wikipedia context, and now a new document with some new event or new information comes in, which is relevant to this summary, then can you generate the update and only the update based on the news article as well as the Wikipedia context? And so we have designed a task to perform content transfer from an unstructured source of information, and we have released a huge data set to perform this task. Some of the applications of this particular task is that you can use it to update software documentation when new requirements come in. Or if you're maintaining a summary of your inbox of a particular thread and now a new email comes in for that thread, then can you update the summary of your inbox? Can you update legal documents when new laws are passed or amendments to the new laws are passed? And can you update Wikipedia articles when new events occur in the real physical world? So how we create the data set is that we parse through Wikipedia, and the moment we hit a reference link, the sentence before the reference link is considered as the update that we want to generate, and 3 sentences before the update are considered as Wikipedia context. We search for this reference link in Common Crawl. This was done to maintain reproducibility. And we retrieve the HTML of the news article from Common Crawl. We further parse this HTML to get plain text of the news article. And now we are left with tuples of news article mapped to the Wikipedia context, mapped to the update which came from the news article. And we have a total data set size of 636,000 instances. So I will quickly go over the models that we build, and this is because they are all, so we have generative models and extractive models. All of our generative models use global attention. They are all simplistic models, and I don't want to spend too much time on them. But it was to draw 2 inferences. First of all, whether Wikipedia context helps or not. And if not, then whether this task can be solved as a simple summarization task. And secondly, how far can extractive models alone go in trying to solve this task? So the first is context agnostic model. This is the baseline. This does not get access to the Wikipedia article. And this is a simple sequence to sequence model. You encode the news article and you condition the generation on the encoded vector of the news article. We have the context informed model, which has access to the Wikipedia article. We simply concatenate the Wikipedia context to the news article and encode the concatenated vector, and the generation process is conditioned on this encoded vector. And finally, we have the context receptive model. That is, we have 2 separate encoders to encode the news article and the Wikipedia context. The encoded vector of the news article is used to condition or initialize the decoder, and the encoded vector of the Wikipedia context is given as an additional input at each time step of decoding. And so here are the results on automated metrics. We also present the blue and meteor numbers in the paper, but they follow the same distribution. Here I show you the rouge L numbers. So first of all, we see that models which have access to Wikipedia context perform much better than the models that don't have access to the Wikipedia context. And so this cannot be solved as a summarization task. Second, the generative models perform much better than the simple extractive models. But we have an oracle model, which is like a cheating model. It was designed to set an upper limit achievable by any extractive technique. And this is because we use the same metric, rouge L metric, to first select the best scoring sentence from the news article. And that would be given as the update sentence. And finally, we score the entire data set on the rouge L metric based on the selected sentences. And a scale of 30 and a score of 30 on a scale of 100 tells us that this task is not going, you cannot solve this task using only extractive techniques. We also perform relative human evaluation and of two types. First is close to reference, that is how close to the reference is the generated sentence. And remember that the information in the reference may not be the only salient information in the news article that was coherent to the Wikipedia context. And that's why we perform the second kind of evaluation, that is coherent to content. And this was to reduce the reference bias. Both of these studies are done using human evaluation A/B testing, that is human judges are shown two generated sentences in a random order, and they can also pick the third option of neither. As you can see, for both of these tasks, neither option is chosen the most number of times, which tells us that these models have a long way to go. And but remember that the context informed model, that's the model which had access to the Wikipedia context, performs much better than the model that does not have access to the Wikipedia. We also show more human evaluation relevant to the DUC 2007 guidelines, which follow grammaticality, etc. in the paper. And so with that, I finished my segment on content grounded generation. Do you have questions on this? Okay, then I will move to the third segment, which is on. So I'm still audible, right? Just wanted to check.
Yes, you are.
Great. So I will move to the third segment, which is on structure. And in this part, I have not proposed a model to control for structure and generate text which follows a particular structure, but I try to focus on a subtask of structure, which is sentence ordering task. So the sentence ordering task is that if you're given sentences in a random order, then can you predict the correct order of the sentences? So I had given this example in a slide before. So this is the story, and like the story is in a random order, and can you predict the correct order of these sentences? So prior work has designed this as a sequence prediction task. That is, they actually generate the order of the sentences. And we design this as a constraint solving problem. So we contribute a new framing of this particular task. What I mean by that is that if you have n sentences in a document, then you want to predict n choose two constraints. That is, you want to pair each sentence with every other sentence in the document, and you want to predict constraints of the form, whether sentence one comes before sentence two or not. So for example, if you have 4 sentences in a document, then you want to predict 6 constraints. You want to predict that sentence 1 precedes sentence 2. You also want to predict that sentence 1 precedes sentence 3. You also want to predict that sentence 1 precedes sentence 4, and so on. Once you have predicted these constraints, you can build a graph based on these constraints. So if your constraint that was predicted said that sentence 1 should precede sentence 2, then you draw an edge from sentence 1 to sentence 2. Then if you predict that sentence 2 precedes sentence 3, then you would draw an edge from sentence 2 to sentence 3, and so on. And finally, you apply topological sort on this graph that you have constructed to get the ordering of the sentences. And that would be the predicted order of the sentences. So in this talk, I'm not going to explain topological sort, but I'm going to explain how you can learn to predict good constraints. So the first is the BERT-based representation, or the BT sort technique, which leverages the next sentence prediction objective on which BERT was pre-trained. Here you simply concatenate the tokens of sentence 1 and sentence 2 separated by a separator token. And the BERT representation of this concatenated sequence is used to predict whether sentence 1 precedes sentence 2 or not. We also have LSTM-based representation, that is the LT sort technique. And this experiment was done to understand how far we can get without BERT representations and how close we can get to the then state-of-the-art model. So you use an LSTM encoder to separately encode the two sentences and get H1 and H2. You concatenate the two representations to predict whether sentence 1 precedes sentence 2 or not. And our baseline was the state-of-the-art model before this work, which was the attention order network. And as I mentioned before, most of the prior work designed this as a sequence prediction task. So it actually generated the order. And that's why most of these models are hierarchical models, as is the Aon model. So the Aon model gets a sentence representation using an LSTM encoder. It then trains a transformer on top of these sentence representation to get a document representation. This document representation is used to initialize the decoder LSTM and generate the order of the sentences. We also convert this into BERT-based for a fairer comparison. That is, the sentence representations are, the LSTM is replaced by the BERT-based sentence representations. So here are the results on 5 different metrics. And so the first metric is perfect match, which measures the percentage of documents for which the entire sequence was predicted correctly. These results are for the NeurIPS abstract data set. The second is sentence accuracy metric, which measures the percentage of sentences for which the absolute position of the sentence was predicted correctly. Kendall-Tau measures the number of inversions you would need to reach the correct order. Rouges measures the percentage of pairs of sentences for which the relative ordering between the pair was predicted correctly. And LCS measures the longest common subsequence between the predicted order and the reference order. So the first observation is that LT sort actually performs very close to the complex hierarchical Aon model, especially for the pairwise metrics of Rouges and Kendall-Tau. The second observation is that making Aon BERT-based does help it. That is, you get improvement on top of Aon when you convert it into BERT-based. But finally, that BT sort performs the best on all of these 5 metrics and by a huge margin. We have also introduced a new human evaluation for this task to understand how close are the predicted sequences, predicted orders to the gold orders. And so when you compare BT sort with BAON, BT sort gets most number of votes, even more than the no preference option. But when you compare both of them with the gold orders, the gold order gets the highest number of votes, but BT sort comes a little closer to the gold order as compared to the BAON orders. And finally, we have more results in the paper on 3 additional data sets: the SIND captions data set, NSF abstracts, and AN abstracts data set. And BT sort performs the best in all of the metrics on all of these data sets. We have also further shown more analysis, an analysis of the displaced sentences, that is how far from its actual position was the predicted position of the sentence. And this is a little different than the metrics that I mentioned in the previous slides. And BT sort displaces lesser number of sentences and to a lesser extent. We also show an analysis for documents which have more than 10 sentences. And even if BT sort doesn't have a notion of a global structure, that is, it doesn't see all the sentences at the same time, it actually performs much better for documents that have more than 10 sentences. And the difference between BT sort and BAON is actually larger for longer documents. And finally, remember that AOM style models generate the orders. And so there could be a mismatch between the number of sentences that you give as input and the number of sentences for which it actually generates the order. And we have shown an analysis of this percentage mismatch in our paper, but this problem does not arise for our models at all. So with that, I finish my segment on structure. Are there any questions on this?
Hi, Shrimai. This is Alok. I had a silly question. If you go back to the NIPS abstracts again,
Right.
maybe I didn't understand that. It seems like Kendall tau is the number of inversions that you have to do to get back to the right order.
Correct.
And is more inversions good or more inversions bad? I would think more inversions is bad, right?
Yeah, it is more bad.
So I was trying to reconcile how come BT sort has most number of inversions but ranks well on every other metric.
Oh,
I'm trying to reconcile those two things.
No. So Kendall tau measures that, but it's not lower. It's higher the better in some sense. It's then like the formula takes that into consideration. It does 1 minus the number of inversions that you require, and so yeah.
Okay, that explains it. Thank you.
Yeah. Okay. So finally, I'll move to the ethical considerations of controlling style, content, and structure, and also my future work that I see in this space. So again, going back to the question I asked on the first slide, should machines reflect the way humans interact in society? And so throughout my presentation, I have presented some qualities or some attributes of human communication like style, content, and structure that we want to see in our machines. We want our machines to reflect those qualities. But human communication also has other aspects like usage of swear words, obscenity, bias, hate speech, etc. And do we want machines to reflect this? The answer is no. And that's why it's important to understand the broader impact of controllable text generation and how it can be used for both good and bad applications. So for example, if you use controllable text generation to generate persuasive tweets to spread awareness about climate change, where you control the style and make it catchy, you control for the content, and in tweets, there's not much of a structure. But if you control for these aspects and you generate very persuasive tweets, then you can use the same technology to generate persuasive tweets on social media to keep people away from vaccines. And so where does my work fit into this space and where do I see my work going in the future is that I want to ground the ethical frameworks in relevant literature that is outside of AI. So I believe that AI is not the first community to face these questions on ethics. And philosophy of ethics has existed for hundreds of years. And so we should look at relevant literature outside of AI to see what are the lessons learned and how we can adapt it to the AI community. And some of the things I am focusing on is the first principles of ethics. So first I'll talk about the respect for autonomy. which is an agent should not adopt an action plan that the agent is rationally constrained to believe is inconsistent with an ethical action plan of another agent without informed consent. And the informed consent part is the most important part over here. And I want to explore how you can use these controllable text generation techniques to interact and convey this complex information in natural language so as to provide informed consent to the users. So an example over here is that imagine Amazon builds a bot to either reject or accept refund applications from the users. And so there is a decision-making process involved. And now the bot made a decision to reject the refund. And now the user wants to know why the refund was rejected. And the bot cannot simply point to the Amazon policies as a response, but should be able to respond in a way that the user actually understands the decision-making process and an explanation to why it was rejected. And so my work in content-grounded generation actually fits into this space, and I can expand it to embed ethics in some of the NLP systems. The second is interactional fairness, which is not a first principle, but it is a sub-principle, and it states that every person deserves respect, dignity, and politeness. And as you can clearly see, my work on generating polite requests fits into this space, and I can expand it to include more aspects and generate sentences that provide respect and dignity to the users. It can also be, NLP can also be used for this principle to detect objectionable content on social media platforms. And once you identify features which you can use to detect objectionable content, you can use the same features to ensure that your NLG systems don't generate objectionable content. And finally, there's the generalization principle, which is actually the first principle of ethics, which states that, and this is a little different than generalizability of models. And so what this says that an agent must be rational in believing that the reasons for actions are consistent with the assumptions of everyone with the same reasons will take the same action. That is, if an agent is provided with one set of reasons or evidence or rationales and it reaches a particular decision, then every agent that is provided with the exact same set of reasons should come to the same action. It should come to the same decision. And this, I believe, connects really well to some of the work that AI2 is doing, because NLP can be used to extract evidence or rationales or reasons from textual content, and these reasons can then be used to make ethical decisions. So with that, I finish my talk, and I will be open to taking questions, but I'll just summarize my work before that. So the key to human-like generations is style, content, and structure. And here are my contributions in each of these individual space. In style, I have proposed a new model for style transfer and new styles like politeness transfer, political slant, and gender transfer. In space of content-grounded generation, I define a new task to perform content-grounded generation from unstructured data. And for structure, I have provided a framing of the sentence ordering task, and which is like the state of the art currently. And with that, I would like to first thank my advisors, Alan Black and Ruslan Salakutinov, as well as my committee members and collaborators, and my master students who have helped in some of the work that I presented today. So thank you, and I'm open to taking questions.
Let's all unmute and just give a round of applause for Shrimai. Great talk, Shrimai.
Thank you.
Yeah. Any questions? Looks like there are no questions. So Shrimai will still be around a little while, like for one-on-ones if anybody wants to sign up. And
yeah, I can probably post the sign up link over here if anyone is interested. So yeah.
okay, great. Thanks a lot, Shrimai.
Thank you.